Euclid and the infinitude of the primes. Okay, and what that means is that there are infinitely many primes. Okay, it's that simple. The Greeks were interested in not just geometric concepts, but they also were interested in the theory of numbers themselves, and in particular, they would have been interested in whole numbers. Whole numbers would have been a serious fascination for them. There was something pleasing about the way they behaved. They behaved in a regular fashion, and Euclid was, I mean, it's not clear whether this was his original proof, but the proof that he gave is definitely a classic, okay? Almost any mathematician can instantly recall this proof off the top of their head. I'm not joking, okay? It's that simple, it's that elegant, but it's something that almost every mathematician can just go, boom, yep, know that one, and they can kind of basically give you the roughed out picture of how this goes. Okay, these are a couple of quotes from the book, a true classic, a mathematical favorite. And it is, for sure, okay? So again, just to remind you, Euclid wrote the elements, and that was divided up into, did I say 12 books? Or I always forget if it's 12 or 13. It's one of those two numbers, okay? Book 1 is what we looked at last week. It focused primarily on kind of setting up geometry of the situation, and started with these propositions and common notions and definitions, and then just built up the basic ideas of geometry from it. Now, one of the postulates, which I said I would tend to refer to those as axioms. One of the postulates was so-called parallel postulate, and that's fairly controversial because it seems to be assuming a lot. And we talked about how when you assume the parallel postulate, you end up with a certain kind of geometry. It's a flat planar geometry, okay? Totally flat. And if you assume a different version of the parallel postulate, maybe even its opposite, you get a different kind of geometry. And if you're interested to know some details about that, you should take geometry with Dr. Fry, and you will look at those different sorts of geometries one can get depending on what you assume at the beginning. The one that you were exposed to in high school is called the Euclidean geometry or planar geometry, like you're in a flat plane, okay? But there are other geometries you get if you assume even the opposite of the parallel postulate, and in some sense, those geometries almost model reality better, which is strange, okay? You've probably heard someone say, hey, space is curved, right? If you kind of go out far enough, it seems like straight lines aren't describing things as well as they should be anymore. And so it's been hypothesized that we probably, in this universe, exist within something that's not a Euclidean three-dimensional geometry, but maybe some kind of hyperbolic geometry or something like that. Obviously, if you try to do geometry on the surface of the Earth, it's not flat, right? It feels like it is locally, but the further out you go, it isn't, right? You start making mistakes if you try to use planar geometry to predict things when you're trying to predict them on the scale from going to the North to the South Pole. And so you need a different kind of geometry to be more accurate, and that geometry is called the spherical geometry, okay? So you would look at all those sorts of things in Dr. Fry's class later on. But what we did is we looked at the proof of the Pythagorean theorem. Do you remember the picture, the little distorted windmill thing? That was pretty cool, okay? Again, the book 1 is from the elements is the best known and most studied of all the books that make up the elements. And I want to talk a little bit about some of the other books. So books 1 through 4 are just the essentials of triangles and polygons. The polygons are just many-sided geometric shapes. Circles and regulars, like regular polygons. Regular means they all have the same length sides and they all have the same angles, right? All the angles are the same everywhere. Like an equilateral triangle, for instance, yes? Or a square. A square is a regular four-sided polygon, okay? So an equilateral triangle is a regular three-sided polygon. In book 2, a little bit of algebra is delved into, and the Greeks were sort of weird. Even when they were doing algebra, they would try to do it in a geometric way. So things like a plus b quantity squared is equal to a squared plus 2ab plus b squared, which you all know that, right? He would have done that using like an actual square. Does that make sense? So he would have like divided it up into like a plus b, and he would have drawn this picture to kind of illustrate that. Okay, something like this. Here, let me kind of draw it on here just so you can see. He would have done something like this. Okay, here's a square. Okay, here's, okay, here is, what am I doing here? Okay, so here's A, here's B, here's A, here's B. What is the area of that entire square? A plus B squared, right? So area equals A plus B squared. But also look at these little sub rectangles and squares that happen to reside within this thing. You know what I'm saying? Let me move this guy out of the way so you can see it more clearly, okay? For instance, this guy right here is A squared. This guy up here is B squared. And what about these two little sub rectangles? AB, AB, yeah? And so you see that this area is also equal to A squared plus 2AB plus B squared. That's what I mean by sort of a geometric rationale for these algebraic identities. They would have seen like, okay, geometry is the king of intellectual disciplines. Let's try to bring everything back to geometry, okay? One of the disadvantages of doing it this way, though, is what are you restricted to? Positive numbers. See what I'm saying here? Yeah. And we know that this is true even if you have everything in sight happens to be negative, or if one thing's positive and the other thing's negative. In book 3, he obsessed for a while about circles and right angles and semicircles. In book 4, he talked about inscribing and circumscribing geometric figures. Okay. The last proposition of the book is to construct a perfect inscribed pentadecagon. Ooh, what is that? Okay. Pentadecagon, I'm pretty sure it's a 15-sided regular polygon. Okay. Circumscribing and inscribing means you like take a circle, for instance. Okay. And inscribing means that you try to put something inside of it that's regular, like a pentagon. Okay. Makes sense? What do you think circumscribing means? Yeah, on the outside, yeah, like this. Okay, and of course, what would he have been obsessed with? I mean, would he have just been like, look, you just take your pencil and draw it? What do you think he would have been obsessed with doing to make sure everything was super precise? Compass and straight edge. Those would have been the tools, okay? It's a famous mathematician that predated Euclid and actually predated Hippocrates, even Eudoxus. So oftentimes thought of as one of the first, real careful thinking mathematicians. But he developed Eudoxus's theory of proportions, okay? Proportionality in terms of like that would have been the precursor for similar geometric shapes. Preservation of proportions, like this side to this side is to over this side is to this side over that side, right? So Eudoxus's theory of proportions would have been a heavy concentration point for Euclid to that end. Any questions on this so far? This is just kind of an overview of what the first 6 books of the Elements was about. All right. Oops. Okay, let me see here. All right, on to books 7 through 9. Okay, that's where he starts talking about number theory. Okay, and number theory is something very specific. So like when I say number, typically you mean counting numbers. Okay, you mean and maybe integers. So this would have been things like 0 plus or minus 1 plus or minus 2, etc. Okay, whole, you know, like the integers. Sometimes people call these the whole numbers. Technically, the whole numbers are just 0 and all the positive integers. Okay, but number theory is acutely interested in trying to understand integers well. If you can't understand integers, then what chance do you have of understanding anything else about numbers? Do you know what I'm saying? Integers are the basic elements to understand numbers on the whole, right? On the whole real line, for instance, okay? And in particular, in number theory, you're obsessed with primes because primes are the building blocks of integers. What's a prime? That's right. It's a number that's only divisible by 1 in itself. So it's only, it doesn't have any, it doesn't, like its only factors are trivial, namely itself and 1. Those are the only factors it has. The other, like, and what do you call something that's not a prime, do you know? Composite, right? And that makes sense if you think about it. Composite is like it's composed of something. Yes, it is composed of smaller primes that build it up, yeah? He introduced something called the Euclidean algorithm. He didn't call it that, obviously. But what it was is it was basically, and incidentally, if this interests you, number theory, we have a class called number theory that you can take, right? So all of the stuff that we're talking about right now resides in the specific discipline of number theory in mathematics. It's the study of integers. And the Euclidean algorithm was basically a glorified division algorithm that led you to the greatest common divisor of two integers. Does that make sense? The greatest common divisor. That is the largest thing that divides into both of the numbers you started with. That's what the greatest common divisor is. And then in book 9, proposition number 14, he proved something called the fundamental theorem of arithmetic. Okay? That is a very big deal, and you use it all the time. Basically what it says is, if somebody gave Monique and I a number 2 factor, okay? And Monique went to Chick-fil-A and I went to Chuck's, and we toiled over the number that we were gonna factor in 2 primes. And then we reconvened later on, what would be true about our factorization of that number? It would be the same. Does that make sense? Like that, like it would, there is, what the fundamental theorem of arithmetic says is, it is possible to factor a number into primes, and how many ways are there to do it? 1, okay? There's exactly 1 way to do it. So that's what the fundamental theorem of arithmetic says, okay? So Euclidean algorithm, right? This guy right here, you know, helps us find GCDs. And the fundamental theorem of arithmetic, this basically speaks to unique factorization into primes. Only 1 way to do it, okay? Okay, any questions on that so far? Okay, moving on. Here we go. So remember, what is it that we wanted to prove? Well, we wanted to prove that there are how many primes? An infinite number, okay? So we've already talked about the definition of prime and composite. Okay. There is a proposition I want to talk about. It basically says that any composite number, and we're using Euclid's like awkward language here, any composite number is measured by, that is divisible by, some prime number. Okay? So if you start with a number bigger than one, an integer bigger than one, and incidentally, when he says number, he's talking about a positive integer in this case, yeah? Any composite number is measured by some prime number. It means I can find a factor of that thing that happens to be prime, okay? And let me just kind of talk you through how that proof goes. Are you ready? Okay. So start with a number a greater than 1, okay? If a is prime, done. You know what I'm saying? If a is prime, we're done. If not, so let me just say a greater than 1. If a prime, done. Because look, I said any composite number is measured by some prime number, okay? So like if a is a prime number, there's nothing for me to do. It doesn't even meet the qualification. Like we're talking about composite numbers, yes? So what may we assume at the beginning? So if a is composite, what? What does that mean? What does it mean for something to be composite? It's not a prime. It means it has a factor, yes? That's not 1 and not itself. Okay, then A has a factor B with A greater than B greater than 1. Do you know what I'm saying? Yeah? So A is going to be equal to B times something. And by the way, there's some notation in number theory for that. What we would say here is that B slash A, all right? So what this means is B divides or is a factor of A. That's what that notation means right there, okay? Okay, if B is prime, guess what? We have found a prime factor, correct? Or else what? If B is prime, what? Are we done? Done. What's the only other possibility? Yeah, if B is composite, what can we do? There's another factor between B and 1. Does that make sense? Okay. B has a composite, or B has a factor, sorry, not a composite factor. B has a factor C with what? I'm going to write it down here with, what's the deal? A is greater than B, is greater than C, is greater than what? 1. Do you see what's happening here? And you just keep going. Okay? So let me just kind of go up here. So eventually, what are we going to get? Eventually, we get A greater than B, greater than C, greater than D, greater than right? Greater than 1. And you realize these things are decreasing with each one of the steps, yes? So this has to terminate somewhere, yeah? Okay, this chain will terminate in a what? In a prime that divides everything. It divides the thing before it, the thing before that, the thing before that. Like, because all of these things are factors of each other. Does that make sense? So this thing will divide A. And that is the end of the proof, QED, right? We're going to use QED so that we can promote our math organization. Yeah, okay? It's a fairly simple proof, but basically what we have here is kind of a chain of divisibility that can't keep going down forever, yeah? That chain of divisibility has to terminate in a prime because the numbers keep getting smaller. Does that make sense? Yeah? So that's the essence of Euclid's proof that every composite number has a prime factor. And that's basically the first step toward the fundamental theorem of arithmetic. If you want to make a claim that every number can be factored into a product of primes uniquely, then you better know that every number actually has a prime factor. Yes? That would have to be true. Okay. Any questions on that? Any questions on that? Let me move this so you guys can see that, right? A greater than B greater than C greater than D, etc. That chain has to terminate in a prime that divides A. Okay. The other thing that you need is the following. Okay, remember what does this little slash mean that I have written right here? These slashes. Divides. Yeah? And I've even started, I didn't use the wedge, but I put and. Like we have some logical statements here. If I have a positive integer that divides m, and that same positive integer divides n, then that same positive integer will also divide the difference between those two. I won't go into the details of that. That's pretty easy. Here's why. Basically, imagine that g was 5. What this is saying is, if 5 is a factor of one number and 5 is a factor of another number, then 5 will also be a factor of the difference. Does that make sense? Okay. Because you could kind of factor out 5. Does that make sense? And 5 will be a factor of that difference, yes? So if I start with two things that have 7 as a factor, guess what? Their difference will also have 7 as a factor. See what I'm saying here? Okay? All right. Those are really the two ingredients, two very basic ingredients. One is that any composite necessarily has a prime divisor. The other ingredient is if two things have a factor in common, then their difference has that same factor in common. That's what this is saying right here, yes? If two numbers have a factor in common, then their difference will also have that same factor in common. And so will their sum, by the way, yeah? Okay. Any questions about those two little ingredients that we're going to be using here? Any questions about that? All right. Are you ready? Let's do it. Here's proposition 9, book 9, proposition 20. Prime numbers, this is how Euclid said it, Euclid of Alexandria. Prime numbers are more than any assigned multitude of prime numbers. That's a weird way of saying, guess what? The primes are inexhaustible, right? The primes themselves are inexhaustible, okay? There's an infinite number of them. Okay? And actually the proof is very, very easy. And there's like, I actually have a linked website in here that kind of takes you to just the thinking. It's very basic, and we'll talk through that a little bit. But you'll see what those two main ingredients are that kind of constitute the proof itself. He basically uses something called a reductio ad absurdum, which is a Latin phrase. Means we're going to reduce this to an absurdity. It's basically called a proof by contradiction, which we'll talk about later. What you do is you kind of assume the opposite and show that you end up with something ridiculous. And therefore, it was stupid to assume the opposite of the original thing. That thing must have been true. Does that make sense? So like, I have something I want to prove, namely that primes are infinite, the number of primes are infinite. So the way he's going to prove it is he's going to start by assuming what? That they're not infinite, namely that there's some bounded number of them. And what he's going to do is show that something ridiculous happens. It's impossible. And therefore, what was the stupid thing that got us into that mess? Assuming that the primes were finite in quantity, yes? Therefore, the primes must be infinite in terms of their quantity. Okay? So here's, okay, well, hang on. Here's the website I was talking about. I'm going to go to this first. Okay? Yes. So here's, oops, this over here. Okay? So reductio ad absurdum. Let's kind of just read through this together. So here's how we started. Assume there are a finite number, n of primes, the largest of which is Pn, okay? And by the way, so he kind of imagines that there's little n primes. So P1, P2, etc., Pn, okay? He would have probably written them differently. He would have just said, you know, A, B, you know, dot, 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 D or something. No, but he would probably use Greek letters or something, okay? Obviously. Okay, so here we have n total primes. We're assuming that this is all there are. N could be a trillion, but we're assuming that eventually we've just exhausted the number of primes, okay? Okay, so again, do you see he's assuming the opposite of what he wants to prove? Yeah? He assumes the opposite to be true, and he's going to show that something outrageous happens, okay? Consider the number that is the product of these plus 1. Got it? Consider the number that is the product of those primes plus 1. Okay, so like if our list was just 2 and 3, for instance, like there's examples down here. If our list just consisted of 2, for instance, he's saying take 2 plus 1. That's 3, right? If our list was just the prime numbers 2 and 3, what would he do? Multiply 2 and 3 together and then add 1. Does that make sense? Okay. If our list consisted of just 2, 3, and 5, then what he's saying is take 2, 3, and 5, multiply them together, and add 1. Yeah? So he's forming this special number right here that happens to be the product of all the primes, and adding 1 to it. Okay? Now, here's the thing. Is that number divisible by any of the primes? Why not? What's the remainder going to be? Think about it. What is the remainder? If I were to divide by P1, for that number n by P1, what would be the remainder? 1. You see it? Because it's P1 times something plus 1. The remainder would be 1. Okay, so let me just say, to add to this, n has a remainder of 1 when divided by any of these things, P1 dot 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 through Pn. Okay, well that's interesting. Hence, what are the possibilities? Either n is itself prime, but n is already bigger than all of the previous primes. Do you know what I'm saying? It's the product of all of them plus 1. It's bigger than all of them. Okay? So hence it is either itself prime, which by the way would contradict our assumption, yes? So if it is itself prime, that would be a contradiction. Why would that be a contradiction? Why would that be a contradiction? Right, because we assumed we had a complete list of primes and we just would have found a new one. Does that make sense? Or it's divisible by another prime greater than Pn. Because what did we say had to be true about every number? If it's not a prime, it's composite. So if n is not prime, it's composite. And what do we know about every composite? It's divisible by some prime, yes? But is it divisible by any of these primes? No. So there would have to be a prime not on the list that divides evenly into this. Does that make sense? So either n itself is prime, which is a problem, or it's divisible by some other prime by that proposition we just proved a couple of minutes ago. But it couldn't possibly be any of these primes that we have. Make sense? Either way, we stumble upon a brand new prime. Does that make sense? Either it's itself a prime or it's divisible by a prime. Yes? Yeah, that's exactly right. Yes, yes. But all the Euclid did was, you're right. Because, you know, if a composite is divisible by one prime, then clearly it's divisible by two. Yes, you're right. You would get at least two primes. That's a great observation. Yes, yes, sir. No. 65. Yeah. Yeah, that's right. So these guys are all like, I could say, you know, this guy's less than this, less than, right? So these are all kind of an increasing order or something. Yes. Okay. So does that make sense? He started by assuming he had a finite list of primes. He makes this number by multiplying all those primes together and adding one. Excuse me, that thing is not divisible by any of the other primes. It has a remainder of one if you divide it by any of those previous primes. So there's only two possibilities. Either this number itself is prime, and hence will be a brand new prime, because it's not any of the other guys, yeah? Or what? It's divisible by a prime that's not on the list, yeah? So either the number itself is a new prime not on the list, or it's divisible by a prime not on the list. Contradiction either way. Yes? It's a contradiction either way. Yeah. Well, okay, so what we don't know, so here's what's interesting. That's a great question. There are no known, like we only know of a finite number of primes. Does that make sense? We know there are infinitely many of them, but then we start trying to catalog and list the primes. Okay, and you know, these computing eggheads are constantly trying to find the next prime on the list. Does that make sense? So they have machines running all the time trying to check all possible factors and come up with the next prime. But they know they're never going to be done. That makes sense? So here's what's known. Or look, there is no known infinite family of primes. Like we know there are infinitely many of them, but the numbers that we actually know to be prime at the moment, that is a finite list. Does that make sense? Yeah, but there are infinitely many of them out there. We just haven't found an infinite number of them. And nobody's proved, hey, everything of this type is a prime, so here's an infinite family of primes. Okay, so that's what they're talking about when they say that. They've basically found the next prime to put on the list. And incidentally, all of cybersecurity depends on multiplying two prime numbers together, large prime numbers. But the issue is, it would be stupid to use two numbers that happen to be on the known list of primes. So it turns out that all of the cybersecurity implementations use things that are highly likely to be prime. They're called pseudo primes. And they use those to implement their systems because any hacker could just go to the list of known primes and just try them all and then crack your system. Does that make sense? So in the system, they have pseudo primes, things that are highly probable to be prime because lots of things have been checked as possible factors. Yeah. Because the number theory doesn't work unless you have just two primes multiplied together. We'll actually look at that. We'll look at something called RSA cryptography, and you'll see that the math doesn't work unless you start with two primes. If you end up with, you know, if you take like 9 and 25 or something like that and multiply them together, the math won't work out. It's a good question though.
Why does it?
Questions on Euclid's proof? Does it make sense?
I have one question.
Beautiful.
I have a question. Um,
Okay, so either in itself is prime, or what? Or it's composite, and hence will be divisible. Like what we said is we took P1 through Pn to be the primes in order. Does that make sense? But or it's divisible by another prime not on the list. And because we've taken the n smallest primes so far, it must be like one that happens to be larger than Pn itself. Somebody was asking a question online.
yeah. So
Yeah.
I was wondering why it said another prime greater than p sub n, because I was thinking like if you had 3 and 5, 3 times 5 plus 1 is 16, and the prime
Well,
factor
yeah,
that would be q, which is
right.
less
So
than 3.
John, we're assuming that this is somebody, yeah, somebody just asked this out in the, so you guys are thinking the same thing. So what we do is we start listing the primes, and the list it kind of accumulates. You start with 2, then 2 and 3, then 2, 3, and 5. So we're assuming that list consists of the n smallest primes. Does that make sense?
Yeah, that makes sense.
So like the next one, you know, a prime that would divide that product plus 1 couldn't be one of those primes. It would have to be one that's actually bigger than that list of primes. Okay? But I have a question for you guys. Do you think you always get a prime by just multiplying the numbers together and adding 1? Do you think you always get a prime? You don't, because, okay, and that's why I like this little website. Look, they actually, I mean, here's the little surprise. See what they're doing? They go 2, and then they go 2, 3 plus 1, that's 7, that's a prime. 2, 3, 5 plus 1, 31, that's a prime. 2, 3, 5, 7 plus 1, that's 2, 11, that's actually prime. 2, 3, 5, 7, 11 plus 1, 23, 11, that's actually prime. But then suddenly when you get to 2, 3, 5, 7, 11, and 13, multiply those together and add 1, you get 30,031. That's what our capital N would be in that case. And either N itself is prime, or it has a prime divisor that is bigger than all of those other ones. And in that case, that thing breaks down into 59 times 509. Yeah? So you can see both of those cases. It's weird that it takes that long to emerge, but it does by the time you multiply up to 13. Yes? Maybe. Yeah. Yes. Mm-hmm. Yeah, I think it would be. Yeah. So look at that gnarly thing right there. Look at number 12. Right? So you multiply all the primes up to 37, you get that disaster. Let's see, what number is that? Million, billion, 7 trillion, 420 billion, 738 million, 134,811. Nothing factors like that. Okay? Notice all of those factors are primes bigger than the things on the list. Okay? All right? Any other questions on that? Yes.
So multiplying primes at 5 different time than anyone doesn't always equal time. But it's still, I probably don't think that, oh, maybe like it stops eventually, so they are.
How come you don't think what?
Like how does he know that this doesn't always equal time? That like what if ends and then figure it would stop? Like how does someone think that?
Well, because I mean, look, okay, so look at number, just look at number 6 right there. So what we've said is, look, 2, 3, 5, 7, 11, 13. Is that all the primes there are? Well, I don't know. Let's multiply those together and add 1. What do we get? 30,031. So what he's saying is there's 2 possibilities. Either that thing is itself a prime, and it's clearly going to be bigger than anything on the list, or what? Or it's divisible by something that's a prime that isn't among those things that I multiplied together, because we know that when I divide by any of those things I multiplied together, I get 1 as a remainder. It doesn't divide in perfectly. Does that make sense? Okay. So I'm going, and so look, since I took the what is it? That's 6, the 6 smallest primes. I know that it can't be, like whatever prime divisor I have can't be among those. So it has to be a new prime, not on the list, that's actually bigger than all those. Yeah. Yeah.
And then
Yeah.
you get to the 30,031.
Uh-huh.
It's like, well, either this is a prime number, or
Yeah.
it's bigger, or it's got another factor of a prime number that's bigger than
Yeah, that's right. Yeah. Yeah. But in this case, in number 6, little n is 6, right? Little n is 6 because there are 6 primes so far, right? And big N is 30,031. And what you're saying is either big N itself is prime, or it has a prime factor that must be necessarily bigger than all of those ones that are on the list so far, because those ones are the smallest ones. Does that make sense? And so he was just careful to make sure, look, I've taken all the smallest primes so far. And what John was doing is he was saying, well, look, if you go 3 times 5, like suppose your list was 3 times 5. If I have 3 times 5 plus 1, what's that? What number is that? And that's divisible by a prime, but that prime is actually smaller than 3 and 5. Does that make sense? But what Euclid did is he made sure to multiply all the smallest primes together so that the next prime was guaranteed to be bigger and off the end of the list. Okay? All right. I'm going to go back. Let's see here. Where is my... Okay. How do I get out of here? Oh, here we go. Okay. You guys ever heard of something called twin primes? Twin primes are pairs of primes that are 2 apart. 3 and 5. 5 and 7. 11 and 13. 17 and 19. One of the biggest prizes in all of number theory has been, hey, it seems like there's a lot of twin primes, and it seems like if we go out far enough, we always like stumble upon these twin primes. So again, twin primes are primes that are how far apart? 2. So the question that naturally arises, we just talked about there being infinitely many primes, but the question has become, and the Greeks were talking about this, and we are still talking about this. Are there infinitely many pairs of twin primes? Okay? Are there infinitely many pairs of twin primes? Guys, that has been an open question for since the beginning of time. But in recent years, there have been massive advances in this direction. And there's a little link right here. This is a very interesting story. This is a great article from Slate, but of course it has the obligatory random cuss word in it, which I don't understand. But this is one of the best articles I read on the topic. This guy right here, his name is Yitang Zhang. He goes by Tom. Okay, Yitang Zhang. He actually was a manager at Subway in New Hampshire, and was an adjunct professor at the University of New Hampshire. And he hadn't published a paper for over a decade, which is academic suicide. I mean, he's never going to get a full-time position if he's not publishing, okay? But he was adjunct teaching at the University of New Hampshire, and he was managing a Subway. And he shocked the world in 2013 by making the first real advance toward proving the twin prime conjecture. What he showed, he didn't prove the twin prime conjecture, but what he showed is that there are infinitely many pairs of primes that are at most 70,000 apart, or actually 70 million, I think. Let me see, I think it's down here. Is it 70 million? I think it's 70 million. Hang on. We'll see here. I'm sure. I think it's 70 million as far as I can remember. Yeah, 70 million. It's right there. The thing is going crazy here, but yeah. Okay, so he proved that there are infinitely many pairs of primes that are at most 70 million apart. And the mathematical world was shocked. No one's been able to prove that there's any bounded gap but he showed that there are infinitely many pairs of primes that are at most 70 million apart. And then there's a really famous mathematician by the name of Terence Tao from UCLA, who's won something called like the greatest prize in mathematics, the Fields Medal. He has a working group. They went and read his proof. Nobody believed that it was going to be a correct proof at first. This guy's managing a subway, for crying out loud, and he makes the first advance in 2,300 years on this problem. Okay? They went and read his proof. They found that it was true, and they actually noticed that he could have squeezed more out of it than he realized. And within 2 weeks, Terence Tao, in conjunction with Zhang and a few of his other friends, had reduced the gap to 6. Okay? So where things stand right now is that there are infinitely many pairs of primes that are at most how far apart? 6. 6. There are infinitely many pairs of primes that are at most 6 apart. So if you go over to Chuck's and you're able to improve that gap to 5 or 4 or 2, I would say that you probably are in line for a Fields Medal. And by the way, you get a nice fat paycheck too. It's $1 million or something like that. Okay? Yeah, you would definitely get an A in class if you did that, for sure. Okay, so there's a link to that article. I would encourage you to read that. All right, we're done.